Imagine spending, I don't know, millions of dollars to build a state-of-the-art municipal water facility for a really remote community.
Oh, yeah. Like flying in all the materials, bringing in top urban engineers.
Exactly. The technology is flawless on paper. The blueprints are perfect. But, a few years later, you are standing there watching this multi-million-dollar building literally sink into the mud.
Just slowly sinking into the ground.
Right. And eventually it's leaning at this severe 20-degree angle until the entire system just has to be completely shut down. It was completely the wrong tool for the environment.
And the crazy thing is, that scenario isn't a hypothetical. I mean, it happens a lot when a new technology arrives with this massive, shiny promise.
Like, oh, we're going to save time, reduce costs, and improve safety.
Right. But it ends up creating dependency or increasing waste, and we see this all the time, solving one problem while quietly creating three more.
Yeah, the unintended consequences. Welcome to this deep dive, by the way. Today, our mission is to unpack Alaska Cultural Standard B4.
Which is such a fascinating framework.
It really is. It's basically all about how we identify quote-unquote appropriate forms of technology and how we anticipate their actual consequences on community well-being. So we're going to be looking at everything from like ancient stone traps to modern wind-powered microgrids.
And as we go through these examples, there's a central question we want you, the listener, to keep in the back of your mind today. And that is, how can a community decide whether a technology truly improves life?
Okay, let's unpack this, because I think before we can even begin to evaluate whether a technology is, appropriate, we have to completely redefine what the word technology actually means.
Because people hear that word and they have a very specific image in their head, right?
Oh, totally. When I hear that word, I immediately just picture microchips, smartphones, glowing screens, the digital stuff.
Which is, to be fair, a very recent and very narrow definition of the word. Technology actually encompasses an incredibly broad spectrum. We are talking about traditional mechanical, medical, environmental, transportation, communication, and energy tools.
It's a huge umbrella.
It really is. Stripped down to its core, technology is basically just the application of knowledge to solve a problem. That's it. And some of the most sophisticated engineering on the planet, honestly, doesn't have a battery, a microchip, or a power cord.
Right. I was actually blown away by the traditional Alaskan technologies we're looking at today. They are absolute masterclasses in structural engineering and biomechanics.
Oh, absolutely.
Like take the ulu, for example. I had no idea about the mechanics of this thing.
The ulu is just a brilliant piece of design. It's a traditional knife with a crescent-shaped blade. Historically, it was made from ground slate or jade, and it has a handle of bone or wood that's hafted directly over the center of the cutting edge.
Wait, so it's not just shaped that way for, like, cultural aesthetics? Because I always thought it was just a style choice. There's an actual mechanical advantage to
Oh,
it.
it's pure physics. It's amazing. Think about a standard chef's knife that you'd use in your kitchen. The handle is off to the side, right? Which means your wrist has to act as a lever. So it's absorbing a lot of torque and strain every time you chop.
Right. Your wrist gets tired if you do it long enough.
Exactly. But by placing the handle directly over the crescent blade, the ulu aligns the cutting edge directly under the user's hand and forearm.
Oh, I see.
So it mathematically multiplies your downward force and leverage. A person can process fish or heavy hides all day long with, minimal strain on their wrist and joints.
That makes perfect sense. The tool does the work, not your joints. You're just pushing down.
Precise.
And then you have the traditional toggle-headed harpoon, which is just as wild. It's engineered so that it has a retrieving line attached off-center on this detachable head.
Yeah, that's a genius piece of tech.
It really is. Once that head penetrates the hide of a marine mammal, the tension on the line causes the head to pivot exactly 90 degrees. It locks completely under the skin, so it simply will not detach no matter how much force is applied.
It's an incredible biological locking mechanism. Or consider snowshoes, which are basically a masterclass in applied mathematics and surface area.
Oh, I hadn't even thought of snowshoes as math.
Oh, they totally are. You take a broad frame, you weave a web of rawhide, and suddenly you are distributing the human body's entire weight over a much wider surface area. It drastically decreases the pounds per square inch, the PSI, on the snow surface.
So you don't sink.
Right. It allows a human being to walk right across deep powder without just immediately plunging down to their waist.
I love looking at these examples because it highlights this vital distinction we need to make today. There is a massive difference between a technology that simply works mechanically versus one that is culturally and environmentally appropriate.
Yeah, and that distinction is everything.
It's like buying a luxury, I don't know, a low-clearance sports car to drive on a muddy tundra trail in rural Alaska. Does the engine work? Yes, the engineering is flawless. It works perfectly.
Right, on a paved highway.
Exactly. But it is completely the wrong tool for the place you're actually in. You aren't going to get 10 feet. So what are the actual factors that decide if something actually fits?
Well, if we connect this to the bigger picture, we have to look beyond just handheld tools and examine community-wide infrastructure. Because when you scale up to something massive like water and sanitation systems, the constraints of place, climate, and maintenance become incredibly unforgiving.
Let's talk about those constraints, specifically the permafrost problem. Because if you want a municipal water system in the lower 48 states, the standard engineering solution is super simple. You just dig a deep trench and bury the pressurized water mains underground.
Which is a technology that completely works down there.
Right, down there. But applying that to remote Alaska is where you get the sinking building I mentioned in the introduction.
Yeah, and that happens because much of rural Alaska sits on permafrost, which is ground that remains completely frozen year-round. So if urban engineers try to apply that exact same trench and bury technology in the Arctic, they are burying a pipe that carries relatively warm liquid water directly into completely frozen earth.
Wait, so the heat from the water pipe itself is what destroys the foundation. It's literally sabotaging its own environment.
That is exactly what happens. The ambient heat from the liquid water thaws the surrounding permafrost. And when that subterranean ice turns to water, the ground undergoes this severe settling.
It just melts away.
Right. It literally shrinks and collapses, which physically snaps the rigid pipes and compromises the foundations of any buildings above them.
Wow, so how do they fix that? I mean, if you can't bury the pipes, how do you keep the water from freezing solid when it's like 40 below zero outside?
So to make the technology appropriate for this specific environment, engineers have to completely abandon that standard underground model. Instead, they use above-ground utilidors. Yeah. These are highly insulated corridors for the pipes, and they're raised up on pilings above the ground. But even then, it's not enough. They have to use electrical heat tape, or they run continuous recirculation loops with glycol heat exchangers, which is similar to antifreeze, just to prevent catastrophic freezing during the winter.
Man, the stakes for getting this right are just incredibly high. There's this case study about the community of Nunapitchuk that perfectly illustrates this. It shows the immediate versus the delayed consequences, really, the trade-offs, when a system fails because it wasn't actually appropriate for the environment.
Yeah, the Nunapitchuk case is a really stark example. In that community, the municipal water system relied on a central washateria facility to provide treated water for everyone.
Right.
But because of that thawing permafrost underneath the foundation that we just talked about, the ground subsided. The entire facility ended up leaning at that 20-degree angle you mentioned earlier.
The 20-degree angle? I mean, you can't safely operate heavy machinery or highly pressurized water systems in a building that's tilted like a carnival funhouse. It shut the whole place down.
Completely shut it down.
And this is where we see a really brutal cascade effect. The intended effect of the washateria was to provide reliable, clean water. That was the goal. But the delayed consequence of its structural failure forced the residents to revert to manual hauling from the river.
Yeah, and using honey buckets.
Which are basically 5-gallon buckets used for human waste inside the home.
And we really have to look at the health data to understand the true cost of that failure. Because the transition back to honey buckets and unpiped water isn't just an inconvenience. It's not just a step backward in comfort.
It's a health hazard.
A massive one. There is a direct statistical link between the lack of running water and elevated hospital visits for severe skin infections, respiratory diseases, and invasive pneumococcal disease, particularly among young children.
Oh, that's heartbreaking.
It is. When the technology fails to fit the physical environment, it rapidly becomes a severe public health crisis.
But wait, I want to push back on the maintenance side of this for a second.
Yeah.
Because someone listening right now might say, well, if the above-ground utilidor systems are so complex with their heat tape and glycol loops, why not just hire a dedicated operator? Like someone whose only job is to run the water plant. Why rely on a local operator who has to leave for hunting season?
I'm glad you brought that up, because that is a very common outsider perspective. People think, just hire a specialist. But it fundamentally misunderstands the economic and cultural realities of these remote communities.
How so?
Well, in these locations, municipal operators aren't just employees. They are also the primary food providers for their families. They absolutely must take time off during these very brief seasonal subsistence hunting and fishing windows.
Right, the seasons don't wait for the water plant.
Exactly. A moose or a caribou harvest can provide a family's protein for an entire year. You cannot simply skip that. It's a matter of survival and culture.
So the technology actually has to adapt to the community's way of life, not the other way around. It shouldn't force the community to stop living its culture just to keep a machine running.
Yes, exactly. If the engineering system is so hyper-complex that standard national certification exams are required to run it, and a local backup operator can't easily step in while the main operator is hunting, the system is fragile.
That's House of Cards.
Totally. What happens if a proprietary pump breaks in midwinter, and it's going to take 3 weeks and thousands of dollars for a replacement part to arrive by a bush plane?
I see. If the primary operator can't fix that pump with improvised local tools like, I don't know, a coffee can, some wire, and basic welding skills, the entire municipal water system just collapses.
And that perfectly defines the distinction between forcing a technology to work versus finding an appropriate technology. An appropriate technology sustains the community's way of life. It doesn't demand the community abandon its seasonal rhythms just to serve the infrastructure.
That makes a lot of sense.
That's
So
very good.
we can clearly see how the physical environment, like the permafrost, completely rejects the wrong technology. But what happens when the physical environment accepts the technology perfectly, but it completely disrupts the social and ecological balance instead?
Oh, that's a great question. To understand that, we need to look at historical fisheries, because they beautifully illustrate the tension of intended versus unintended effects.
Specifically, who actually benefits from a technology and who ends up paying the price.
Right. And we can start by looking at an 11,000-year-old engineering standard.
11,000 years ago. I am still staggered by that timeline. We are talking about the ancient stone and wooden fish weirs, like the ones in Shakeham Bay and Montana Creek built by Klingit engineers.
Yes, absolutely incredible structures.
And these weren't just simple walls of rocks thrown into the river to block fish, were they? I mean, they were a lot more advanced than that.
Oh, not at all. They were mathematically precise structures. These engineers designed the weirs with very specific interstitial gaps, which are just the spaces between the rocks or the wooden staves.
Okay.
These gaps acted as highly calibrated biological filters. They were spaced precisely to allow juvenile, non-target fish to swim right through the weir and escape upstream, while selectively harvesting only the larger adults.
That is so smart. And they even built complex interior entrance funnels where it was hydrodynamically easy for a fish to swim in, but geometrically and physically difficult for them to turn around and escape once inside.
It's brilliant. And the most important takeaway here is how these indigenous engineers defined the core problem they were trying to solve.
Right.
They didn't define the problem as, how do we extract the absolute maximum number of fish today? They defined it as, how do we harvest enough to feed our community right now while intentionally ensuring enough fish escape upstream to spawn and sustain the run for the generations coming after us?
Here's where it gets really interesting, I think, because you contrast that ancient, sustainable mindset with the industrial canneries that arrived much later. The canneries brought in massive timber fish traps, newer technology, certainly, but newer does not automatically mean better.
Far from it. Those industrial timber traps were designed with one single overriding constraint, and that was to maximize short-term catch volume to maximize profit.
Right, it was all about the bottom line.
Exactly. They were devastatingly efficient at extracting biomass from the water, but with zero regard for the future.
I want you to think about the tech you use every day, as a listener. Who is actually holding the remote control? Who actually benefits from the efficiency of these systems? Because in this historical case, the intended effect of those industrial traps was massive wealth generation.
Huge profits.
But the wealth didn't stay local. It went to distant corporations. And who carried the costs?
The local communities carried the entire cost. The unintended but honestly completely foreseeable delayed consequence was a catastrophic crash in salmon populations.
It just decimated them.
And it went beyond just depleting a food source. These industrial traps actively dismantled the indigenous systems of resource governance.
Because it shifted power completely away from the people who actually lived on the river.
Exactly. When local control is removed, the vital feedback loop that protects a local environment is just severed. The distant corporations sitting in boardrooms thousands of miles away didn't feel the immediate sting of the population crash.
They just saw a dip on a spreadsheet.
Right. But the local communities felt actual starvation and immense cultural disruption.
Hearing all this, it might be tempting to walk away thinking, okay, industrial technology is just bad and destructive, and traditional technology is always good and sustainable. But it's not about rejecting all modern tools, is it? I mean, the goal here is disciplined judgment.
Right, what's fascinating here is how today the most effective and appropriate technologies are actually synthesizing the two. They are actively hybridizing Western empirical tools with traditional ecological knowledge, or what we call tech.
Let's look at how communities are doing this right now because energy is a massive challenge in these areas. We talked earlier about the intense logistical isolation of rural Alaska. To keep the lights on, they have historically had to barge in diesel fuel during a tiny summer window when the ice clears.
And it's wildly expensive.
I was reading that this can cost up to $11 a gallon. $11.
Sure.
That is economically crushing for a small village.
It's completely unsustainable. So communities are adapting by building remote renewable microgrids. They are taking their baseline diesel generators and hybridizing them with modern wind turbines, solar panels, and run-of-the-river hydro.
But wait, how does that actually work in practice? You can't just plug a massive wind turbine directly into a small village grid, right? Wind is intermittent. A massive gust comes through, and then the wind suddenly drops dead. Wouldn't that cause the whole grid to surge and just collapse?
It absolutely would. And that's where the integration of battery energy storage systems, or BESS, comes in.
Okay.
These massive battery banks act as a buffer. They absorb the spikes and fill in the sudden drops to keep the electrical frequency perfectly stable. And they take it a step further with something called beneficial electrification.
What is beneficial electrification? That sounds very technical.
It's actually a beautiful concept. When the wind is blowing hard and the turbines are producing far more power than the community's lights and appliances actually need, they don't just ground that energy and waste it.
Okay.
The automated grid diverts that excess wind energy directly into electric thermal heaters for the community's water supply, or into space heaters.
Oh, wow.
Yeah. It seamlessly turns excess kinetic wind energy into stored heat, which directly reduces how much of that imported $11 a gallon diesel they have to burn for heating.
That is brilliant. It's a perfect blend of modern engineering tailored to extreme local constraints. There's another amazing synergy in environmental monitoring that caught my eye, the LEO network, the Local Environmental Observer Network.
The LEO network is a phenomenal example of technology amplifying local knowledge rather than, trying to replace it. Community members use modern smartphones and geographic information systems, GIS, to log real-time environmental anomalies.
Like what kind of anomalies?
They might log shifting sea ice, or maybe a new species of bird that shouldn't be that far north, or diseased wildlife, or just unusual weather patterns that they notice.
It's like looking at the world with two different lenses in a pair of glasses. One lens is a 10,000-year-old oral history of ice patterns and animal behavior, and the other is a modern satellite data feed and a smartphone app.
That's a great way to put it.
Put them together, and you finally have perfect 20/20 vision of the ecosystem. The technology is just the vessel. The data going into the smartphone is powered by centuries of generational observation skills. These observers know the baseline of their environment intimately. When something changes, they spot it immediately.
We actually see that exact same synthesis redefining fisheries management today, too. Modern biologists are now using something called resistance board weirs.
How do those differ from the ancient stone weirs or the massive timber traps we talked about?
So they are essentially an evolution of the ancient sustainable weir, but they're built with modern, buoyant PVC panels that span the river. The genius of the resistance board weir is that when the river inevitably floods and heavy debris like logs come rushing down.
Which would normally smash a rigid trap.
Exactly. But this weir just temporarily planes down under the water pressure. It lets the destructive debris pass safely over the top without destroying the structure, and then it pops right back up.
And it doesn't just trap the fish, right?
Correct. It funnels them through a counting chute, which is often equipped with underwater cameras, allowing biologists to count and monitor the fish completely non-invasively before letting them swim upstream to spawn.
Oh, that's so cool.
It honors that millennial Tlingit legacy of sustainable, careful monitoring, but uses modern materials to survive the floodwaters.
So what does this all mean? We've looked at ancient stone traps, modern wind microgrids, leaning washaterias. How do we actually apply this disciplined judgment to the future? This all ties back to Alaska Cultural Standard B4.
Yes, the framework.
It's a very practical decision framework, really. It's a series of 6 specific questions a community must ask when evaluating any new technology.
Let's walk through those 6 questions because they are incredibly clarifying for anyone, really.
Let's do it.
First, what need does this address? Is the technology actually solving a critical problem, or are we just buying a shiny new toy because it looks impressive?
A great first filter.
Second, does it fit this place? Will it survive the permafrost, the sub-zero temperatures, the extreme logistics, and the physical reality of where we live?
Third, who controls and maintains it? Can we fix this ourselves with a coffee can and the tools we have on hand, or are we going to be reliant on a specialized expert 3 time zones away when it breaks in January?
Such a vital question.
Yeah.
Fourth, who benefits and who carries the cost? Is this technology enriching a distant corporation while placing the environmental and social risks squarely on the shoulders of the local community?
Yeah, we saw how that played out with the fish traps.
Exactly. Fifth, what could happen over time? This is all about anticipating those delayed consequences. What happens 5, 10, or 50 years down the line when the honeymoon phase ends?
And finally, the 6th question. Can the community adapt or reverse the decision if harm appears? If this goes terribly wrong, are we permanently locked in, or can we dismantle it?
Those 6 questions cut right through the marketing hype of any new tech, whether it's rural broadband, telehealth, or a new sanitation system.
The real question is not whether a technology is impressive. The real question is whether it helps the community live well now, later, and on its own terms.
And I want to leave you with a final provocative thought to mull over regarding how dynamic this process has to be.
Okay.
For generations, traditional underground ice cellars dug deep into the permafrost have been the perfect, appropriate technology for preserving subsistence meat like whale, seal, and caribou.
Right, nature's freezer.
Exactly. They required zero electricity and they worked flawlessly for hundreds of years. But today, the Arctic is warming at 2 to 3 times the global average.
So the very ground they are dug into is changing.
The permafrost is thawing. And those incredibly reliable, time-tested cellars are now collapsing, pooling with water, and ruining the critical food supply. It forces us to ask a deeply difficult question.
What's that?
What happens when the climate changes so drastically that a perfectly appropriate 1,000-year-old technology suddenly becomes an environmental hazard? How fast can a community innovate when the very ground beneath them is literally shifting?
Wow. It's a stark reminder that evaluating technology isn't a box you check once and just forget about. It is a constant living relationship with your environment and your community. Thank you for joining us on this deep dive. Take these 6 questions and apply them to the technology in your own life. Think about who benefits, who pays, and who really holds the remote control. Keep asking questions, and we'll see you next time.